Today we're going to look at some of the details of an inverse, and first of all we'll define what the inverse is of a function, and then we'll look at, is that inverse a function as well, and then some of the properties that we get from there. And let's go ahead and look at our nice little common x squared, our squaring function. And let's see. Points for x squared. Well, when x is 0, y is going to be 0. 1, 1, 2, 4. Now, we also want to look at the negative sides, negative x values. Negative 2 also gives us a y value of 4. Negative 1 gives us a y value of positive 1. So, now these are points that represent a function. What's the definition of a function? Each input, each x value has one and only one y value that goes along with it. Now it doesn't say each x value cannot have the same y value. Okay? A function is each x value can have only one y value. It may be the same y value as some other x value. That's okay. That's still a function. Now, we define the inverse as, well, interchanging the x and y. On the inverse, well, these first two, it's going to look real similar. Inverse of 0, 0, well, it's still going to be 0, 0. Flip around the 1 and 1, and you still get 1 and 1. But finally, this next one, we'll see what the inverse does. 2, 4, well, the x value becomes 4, and the y value would be 2. And then the next one, 4, negative 2, and the last one we've listed, 1, negative 1. Now this is what we call the inverse. Now eventually we'll say inverse and we'll mean inverse function. Okay, x squared has an inverse, but is that inverse a function? Well, as we look at the inverse of x squared, here is an input, an x value, that has two different y values. So the inverse is not a function. And a lot of times we try to shorten this up and we'll say, well, x squared does not have an inverse. Well, theoretically that's not quite right. What we should be saying is x squared does not have an inverse function. The inverse of x squared is not a function. But we'll look at a way where we can redefine f of x, redefine what x squared is, so that we can make the inverse a function. But before we do that, let's take a look at a different example. And then we'll take a look at how we find the inverse function. There I go again. It should be inverse function. Let's look at, well, another common function that we deal with, x cubed. And just to kind of give us an idea, points for x cubed Well, again, 0, 0, 1, 1. Well, finally we get to an interesting point. If x is 2, y is 8, and so on. I can't calculate too much beyond that, so. What about negative 1? Well, negative 1 cubed is negative 1. Negative 2, negative 8, and so on. Now, what would the inverse be then with these points? Well, again, 0, 0, 1, 1. The third one, we finally see something of interest. 8, 2 would be the inverse point. Negative 1, negative 1, and negative 8, negative 2. Now, does this look like the inverse is a function or not?
No.
Does each input, each x value, have one and only one y value? Yes, in this case it looks like it. To prove it, we'd have to do more, but just to try to show, well, in the x squared, in the inverse of x squared, we could look at what one, well, we didn't have a negative 1 for the input. Okay. We had 1 and another positive 1 gave us two different answers. 4 gave us 2 and negative 2, but with 8, we get 2, and then negative 8 gives us negative 2. So it looks like this one, the inverse is a function. And theoretically, we could show that, yes, that is the case. And when we look at the graph of this, let's see. I think I'll make unit marks worth 2 each rather than just 1. My graph would be a little not real good with those markings. X cubed, well, we'd have 0, 0, 1, 1, and then 2, 8. And going the other direction, negative 1, negative 1, negative 2, negative 8. So the graph of x cubed looks like that. Well, the inverse, okay, plot these points and see what we get. Well, 0, 0, 1, 1, and negative 1, negative 1. All three of those points are also on the x cubed function. But it's the other points that kind of show the shape of it. 8, 2 would put us here. Negative 8, negative 2 would put us here. And now to see the details, especially in between negative 1 to 1, we'd have to look at a lot more points, but basically we're looking at this graph. That's not right. Yeah, there we go. And it gets really cluttered here. Maybe we'll zoom in and just take a look from negative 1 to 1 and see what's happening. I'll really exaggerate That would be the x cubed part. And then this will be the inverse. Okay. So there is a slight difference in there, but those points will be very close together. Well, since we have shown that the inverse will be a function, what is the equation of that inverse function? To find that algebraically, we'll go ahead and look through this, although hopefully this is review for you. Maybe a long time ago, but that's why I want to make sure we understand how to find the inverse functions. We will be dealing with specific inverse functions with trig functions and a new function called the hyperbolic functions. So we need to understand the inverse functions here. So we have our g of x equaling x cubed. Now the notation for the inverse function is this. Now in algebra, that may look like a -1 exponent. That does not mean -1 exponent. We're not going to have simply 1 over g. Okay, this is special function notation that means inverse function. Now, there's several good ways to explain how this is done. One thing that most students find fairly easy to follow is pretty much change the notation on our original function. Say let g of x equal y. Let your function represent y. And then the inverse process, we flip around the x and the y. Instead of x cubed, we would say y cubed equals the x. So interchange your variables. Now solve for y. Well, y cubed equals x. What do we do to solve for y? Okay, we take the cube root of both sides. Cube root of y cubed is y. So we end up with y equals cube root of x. So g inverse of x equals the cube root of x. And once you kind of see that, that makes sense. G of x equals x cubed. Inverse function would be the cube root of x. And going back to the points we saw, 2, 8, the inverse would turn into 8, 2. Well, the cube root of 8 does equal 2. And even with the negative, we said -2 cubed was equal to -8, which the inverse would be -8, -2. Cube root of -8 does equal -2. So some of the properties that we have with just illustrating these the simple example, we'll take a closer look at the properties. And one of the properties deal with the graph itself. I'll kind of quickly redraw the graph. There's g of x, and then there is g inverse. Now, if these are truly inverse functions, they should be reflections of each other about the line y equals x. Okay. So we should be able to flip one about that diagonal line and be right on top of the other. And yeah, in this case we do. We've got the, I guess this is the inverse. This would be -8, -2, which, flip that around, should end up with -2, -8. Or if we start out up here at our 2, 8, flip that around, that should give us our 8, 2. Every point should work this way. And graphically, it's going to be, like I said, this reflection about this line. Okay. Now, another algebraic property is the composition of these two functions. The function composition with the inverse equals x, and the inverse function composition with the function also must equal x. Both directions give us x. And as we look at this, again, fairly obvious once we understand the composition. G composition, G inverse, means G of G inverse of x, which we said G inverse of x was the cube root of x. And we plug that into G, the cube. So input of cube root of x into the cube function, cubing the cube root does give us x. Well, it's got to work both directions for this to for these to be inverse functions. So flip it around, and we take G inverse of G of x. So this time x cubed is the input, and we input that into, the cube root. G inverse is the cube root. So input x cubed into the cube root of x cubed is also x. So algebraically, x cubed and the cube root of x works. Graphically, x cubed and the cube root of x works. So we're illustrating that both of these are inverse functions of each other. Now let's take a look at something that we've got to be careful with. A fairly common function, but we've got to make a few adjustments to show what the inverse function is. Let's look at the function square root of x. Well, immediately we should recognize we've got a restriction on this function. What can we say about the domain? Okay, cannot be negative. So x goes from 0 to infinity. Including 0, x can equal 0. And as we graph this, well, x equals 0, we get 0. X equals 1, we get 1. X equals 2, well, we don't want to do 2, but square root of 2, that's still a valid point. Square root of 2 is about 1.4. We could show that on the graph, but I'm going to keep it the nice numbers. X equals 4, y is going to be 2. And the graph of this looks like that. Okay. So we do have a function here, And we will be able to say it has an inverse function. Now, I hadn't mentioned that before, but the function, a property called one-to-one, if a function is one-to-one, then it's guaranteed to have an inverse function. Or we would say the inverse of the function is also a function. A one-to-one function says not only is it a function where each input has one and only one output, but we can also flip it around. Each output has one and only one input. Now, this is a very informal definition, but back when we were looking at x squared, we saw 2, 4, and negative 2, 4. Okay. Each input had one and only one output, so it fit the function definition. But those 2 points right there would not fit the one-to-one function, because the output of 4 would have an input of both 2 and negative 2. So that function would fail to be a one-to-one function. And that would also make it fail to where the inverse is not a function. If a function is one-to-one, then the inverse is a function. We're guaranteed that. And in this case, well, functions, you might have been told, we can see the graph is a function by using the vertical line test. Okay. Each x value has one and only one y value. Well, for a function to be one-to-one, it also must meet the horizontal line test. Each y value, each output, can have one and only one input. So whatever point we want to look at, horizontal line, we're also only getting 1 point from that. Now, contrast that with the x squared horizontal line. Maybe this is our y value of 4. We see 2 different x values. X equals 2, x equals negative 2 gives us that same y value. So x squared is not one-to-one. Okay. Well, back to our specific function here, f of x equals the square root of x. We can see it is one-to-one, so we're guaranteed that it has an inverse function. So let's see what that inverse function is.
Berger says do the horizontal line test. Isn't that basically what it is?
Yeah. The one-to-one, to see whether a function is one-to-one, all we have to do is horizontal line test. So we've shown several different things. Square root of x is one-to-one, so we will find an inverse function. Now, to do that, my approach anyway, change f of x to y, and then we need to interchange the x and the y. So it's now x equals square root of y, and in finishing this out, y will equal what? Okay, y equals x squared. Now, We may have a slight problem here if we say the inverse function is x squared. Okay. Because x squared, well, we know the graph. We can take a look at the graph. We said the square root of x looks like this. X squared looks like this. Is that the reflection about the line y equals x? Well, part of it is, but what about this part? There's nothing over here to reflect it. Just forget about it. Well, yeah, we need to do that, but we need to show how we can just forget about this part. Well, we said earlier the domain of f was from 0 to infinity. And the range, we didn't mention this, the range of square root of x would be what? Okay. Would also be from 0 to infinity. We cannot have a negative output from a square root. So, now there's a property for inverse functions. The domain becomes the range of the inverse function. And vice versa, the range of f becomes the domain of f inverse. So the range of square root of x becomes the domain of x squared in this case. So what we have to do is define the inverse function with a restricted domain. So we're saying if f of x equals the square root of x, then f inverse equals x squared if x is greater than or equal to 0. It's not going to work for all real numbers, but it will work for 0 on out to infinity. And again, that restricting the domain there, that domain is the same as the range of f, and the range of f inverse is also the domain of the original function f. Now, does that fit our other properties? Graphing, well, once again, graph of f, graph of square root of x looks like this. Graph of x squared with this restriction would be, well, from 0, 0, 1, 1, it's going to look like that. And restricting the domain that way, we do fit the inverse function graphing property. Okay? Questions there? Now, does it fit the composition, the algebraic property? I guess we should say, does f composition f inverse equal x, and vice versa? We'll go both directions to show this. Well, f composition f inverse, f of F inverse F inverse being x squared. Now, when we go through this algebraically, we don't need to worry about the domain, but it will match the domain. And take the square root of x squared. Well, this becomes a problem if we don't have the domain restricted. Technically, square root of x squared equals what for any x? Technically, this equals the absolute value of x. Think about numerical values. X equals 3. Well, square root of 3 squared, is going to be 3. So in that case, square root of x squared does equal x. But what about negative 3? Square root of negative 3 squared, well, square negative 3 and we get 9. Square root of 9 is 3. We started out with x equals negative 3. There's a case where square root of x squared is not equal to x, but it does fit absolute value of x. Now, this is where we have to go back to our restriction on F inverse. We are saying x is going to be 0 or any positive number, and the absolute value of 0 or any positive number is going to be x because x is greater than or equal to 0. We couldn't say that if we were just looking at x squared in general. But we've got x squared with a restricted domain, so that does show F composition F inverse is equal to x because we do have that restriction on x. Well, the other direction, this one isn't quite as exciting. Yeah, I know you guys thought this was pretty exciting up here. But F inverse composition F, well, F is the square root of x. So plug that into the F inverse, plug that into the square. Square root of x squared, well, that is x. No matter what x is. Of course, x has to be positive if it's under the square root, I guess, or 0, but non-negative. So, both directions of our composition property works. So we're showing the inverse function of the square root of x is x squared if x is greater than or equal to 0. So let's turn it around. What if we start out with x squared as long as we define x to be greater than or equal to 0? F inverse, we could go through the process and all, but we would know F inverse is going to be square root of x. They are inverse functions of each other as long as we restrict the domain of x squared. And that's what your calculator does. On a lot of calculators, the button is one function, and then the second of that same button is the inverse function. I'm not sure on all calculators if square root and the square show up to be the same, but same button, just the second function. E to the x and natural log of x are usually the same button, just the second function. Okay. Questions? Lots of details on the inverse functions. Now we'll go ahead and look at this fancy formula that we're introduced to in the videos. It says if f of x is invertible, which invertible can be thought of as f has an inverse function, or f is 1-to-1. The inverse is a function. A lot of different ways to say that. Then the derivative of f inverse, now all we're shown here is f, and that the inverse of f exists. The derivative of the inverse function, helps if I write the correct notation, not the derivative of f primed, the derivative of the inverse function is equal to 1 over the derivative of the inverse function. Let's take a look at this with our f of x equals square root of x, and again, we know it's invertible. We know that 4,2 is a particular point of the square root of x. So f inverse of 2 will equal 4. Now, as we calculate this then, we need to look at what f primed, what the derivative of our function is, and what's the derivative of square root of x? I think we know that one pretty much by heart. Okay. So the derivative of the inverse function, well, not necessarily at x, but specifically at 2, we can use this formula right here. It's going to be 1 over the derivative of f evaluated at f inverse. So we'll have 1 over 2 square root of, well, our x value
Should be 4.
Okay. I guess we should say our input value, f inverse of 2, which is 4. So 1 over 1/4 is going to equal 4. So not only is the inverse function value equal to 4, but the derivative at that value is 4 as well. Well, think about that. The inverse function is x squared. Derivative of x squared, we know that, that's 2x. And we're looking at x equaling 2. Well, 2 times x, 2 times 2 gives us derivative value at 4, of 4, when x equals 2. So kind of a fancy formula, and of course we're using functions that we know very easily, and this formula really isn't that useful with those functions, but if we get into some ugly functions, inverse functions, we can calculate this same thing using this formula. Very general formula for the derivative of the inverse function. And this week we'll run into some functions that are not quite so easy to work with, and we'll use this idea in finding the derivatives, at least working with inverse functions. So keep working on the worksheets from last week, and tomorrow we'll get a new worksheet.